Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this video, we're going to cap out all of the solving systems with Gaussian elimination and Gauss-Jordan elimination with an application. And this is a very traditional application, but also a very useful application. It's called the traffic flow problem. And in downtown Sacramento, we have a lot of one-way streets. I'm going to make it easy for us, and I'm going to call each street by its color. So we have green street, blue street, red street. We have black street and orange street. Okay. And they're all one ways, denoted by their arrows. So green street goes from left to right. Traffic can only flow this direction, basically, on green street. And blue street, traffic only flows that direction. And so on and so forth, you can see throughout this entire problem. Now, you have probably seen on roadways those little rubber tubes that they lay across the street every once in a while. It's to show or to figure out traffic flow. Now, you may wonder, maybe you haven't wondered, but it is kind of an interesting little thing to note that you don't need to actually place them on every street to know the traffic flow through all the sub-streets contained within a region. All you need to do is have them, if you have a constrained system like this where they're one-way streets, you can just have a strip here, a strip here, a strip here, a strip here, basically at all the inlets and outlets to these streets. As long as you have strips that showcase the traffic flow in and out of this system or network of streets, you can determine the flow at any intersection at any moment. Well, maybe not at any moment, but at least you can determine the daily flow through intersections just based upon where those strips are located. And you can grow this out, by the way. It doesn't have to be just 3 streets crossing 2 streets. You can create your own here, but I'm just giving you a heads up, a little bit of a warning that the more streets, the larger the system. Okay. Now, what we want to know is how many cars there are at any given moment on any given street, or basically how many cars drove down this residential street. Let's just say that's residential street right here. We want to know how many cars flowed through that street during a weekend or something like that, or during a day. Maybe we need to reconfigure where traffic lights are or something like that. So this is definitely a real world style problem. And by the way, network flow like this, or traffic flow, leads to computer problems like network flow, literally. So for a network. Now let's suppose that at the end of maybe a work day or something like that, that we have these numbers of cars flowing through those strips that are on, or driving across those strips that are on the street. So for example, on Black Street, 200 cars cross this strip going south on Black Street into this network. Okay. And again, Green Street, they had 100 cars flowing into their to their street, into this network. Red Street had 120 cars flow in. Let's see. Orange Street had 60 cars flowing in. And Blue Street had 80 cars flowing in. Okay. And then as far as flowing out of the network, Blue Street had 130 cars flowing out. Black Street had 150 cars flowing out. Red Street had 40 cars flowing out, and Green Street had 90 cars flowing out, and Orange Street had 150 cars flowing out of the network. Okay. Now, a couple things I need to assume here. There are no traffic accidents, and that the streets had to be have the same number of cars parked on them. Or let's just pretend there's no parking on these streets. Or if there is, it's the same number of cars that are parked on the streets at the beginning of the day as there are at the end of the day. So in other words, that the net gain and loss comes to 0 as far as the cars going through. So there's no parking, or if there is, people vacate at the end of the day. Okay. The question is, how many cars have flowed through all the sub streets? That is this part of Green Street here. I would love to know how many cars went through here, and I'll call that X sub 1 because we just don't know how many cars flowed through that street. We happen to know that 100 cars are flowing right here through the day, and 200 cars flow through this little chunk during the day. But we don't know how many cars flow through this little leg of it, because 100 flowed in this way, 200 flowed in that way. Not all 300 of those cars went down this street. Some went and continued down Black Street or turned right on a Black Street, whatever it is. Let's see. Also, we happen to know how many cars go here on this street through the day, so I don't need a variable there. There's 150 that exit, 90 that exit this direction, so I don't need a number for that. But I do not know how many cars traveled on this piece of Orange Street, so I'll call that X sub 2. I don't know how many cars traveled on this piece of Blue Street. I'll call that X sub 3. I'll call this X sub 4 because I don't know how many cars flowed through that portion of Black Street. I'll call this X sub 5 because I don't know how many cars flowed through that section of Black Street. And I'll call this X sub 6 because I don't know how many cars flowed through that section of Red Street. And finally, X sub 7 because I don't know how many cars flowed through that part of Orange Street. But all the other parts of those streets I happen to know. So this is going to lead to a system of equations where we have 7 variables. So there'll be a 7 by 7 equation, hopefully. System of equations, that is. All right, so how do you create this system? It's a big question that most people ask when they're doing a problem like this. And the answer is set up via intersections. I really need to know, because these, for example, these 300 cars coming in from the west and from the north here, we don't know which way they turn at those intersections, but we know they all meet at those intersections. So I need to know, I can build an equation just for that intersection. In fact, let me write that down below. I could say, well, in that first intersection, in fact, I'll call that intersection 1. In intersection 1, we had 100 cars coming in from the west, plus 200 cars coming in from the north, and that should be the same as the number of cars exiting to the east, plus the number of cars exiting to the south. That should make sense. Now I'll just go clockwise here to the next intersection. So at this next intersection, which we will call intersection 2, how many cars are flowing into this intersection? Well, X sub 1 of them flow in from this direction, and X sub 2 of them flow in from the south. So the inflow for intersection 2, so the in versus out is what we'd call that. The influx would be X sub 1 plus X sub 2. The outflow, well, 150 cars definitely went north, and 90 cars went east. Okay. And then we get to the next intersection. Again, I'm going clockwise here. So let's go ahead and do that. And by the way, I just made up these numbers. So if my answer ends up being a fraction, I apologize. Those are motorcycles. Okay, so anyway, at this next intersection, which we'll call the third intersection, what's flowing into that? Well, we have 80 cars flowing in from the east. And from the south, we have X sub 7. And then flowing out of that intersection, we have X sub 2 going to the north and X sub 3 cars going to the west. And you continue this process. So, intersection 4. Let's go ahead and do that. Okay. And intersection 4, we have inflowing 60 and X sub 6. And outgoing, we have X sub 7 and 40. Yep. And then the next intersection right here, this bad boy right there, we've got, and what do we call that? 4, so we'll call this intersection 5. At intersection 5, going into that intersection, we have 120 from the west and x sub 5 from the north. Flowing out of that intersection, we have x sub 6 going east and 150 going south. And finally, at this final intersection right here, the 6th intersection, we have x sub 3 and x sub 4 cars flowing in. So 6th equation is x sub 3 plus x sub 4. And flowing out of that intersection, we have 130 and x sub 5. Now, I do want to mention that normally in a textbook, you'll be given something like, let's do this one. You'll be given a grid of 2 streets, right? 2 going east-west and 2 going north-south. And you'll have 4 unknowns that you can see on this screen. Maybe I should zoom in a little bit. Okay, so you have 4 unknowns. In this case, they would be x3, x5, x6, and x7. And you have 4 intersections. So you'd have 4 equations, and 1 for each intersection, and 4 unknowns. It would work out perfectly. In this case, we have 3 streets going east-west and 2 streets going north and south. So we have 1, 2, 3, 4, 5, 6 intersections, but we have 7 unknowns. This is called an underdetermined system. It's still okay. We can still set this up and try to use Gaussian elimination. It's just that we'll have a free roaming variable here. So we'll have one variable we don't know anything about. That will lead to a parametrized solution, but that will also allow people to say, okay, well, we know where to place our extra strip, for example. So the first thing you're going to do to start to build this system is move all variable terms to the left-hand side of these equations, all the constants to the right-hand side. So I will quickly do that. And I'm also going to line things up. Well, no, I think that would be actually hard to do in this case. So this is going to be x sub 1 plus x sub 4 is equal to, we already had it kind of set up, 300. And the next equation, again, x1 plus x2 is equal to 240. The next equation, we get x2 plus x3 minus x7 is equal to 80. The next one, we will get, let's see, maybe I'll keep x6 positive. x6 minus x7 is equal to a negative 20. So I just moved things around there. Next one, I will get x5 minus x6 is equal to 30. And finally, I get x sub 3 plus x sub 4 plus minus x sub 5 is equal to 130. All right, now we're going to set up our augmented matrix. And remember, when you're setting up an augmented matrix, you want columns for each of your variables. So we're going to have an x1 column. I'll just list it right here. So going through these equations, the top equation, I have 1x1. The next equation, I have 1x1. The next equation I don't have. In fact, the rest of the equations, I don't have x1. So I'll write it this way. Since I've given myself well, we have 6 equations altogether. I'll just re-bracket that. Now our x sub 2. Top equation doesn't have one. Second equation does. So top equation doesn't have one. Second equation does. Third equation has one. Let's see. 1, 2, 3. Fourth, fifth, and sixth don't. Fourth, fifth, and sixth do not. Now our column for x sub 3. Again, first 2 equations don't, but third does. So first 2 don't. Third does. Let's see. Anybody else have an x sub 3? Yeah, the last one. And x sub 4 column. Kind of important to line these up. 1, 0, 0, 0, 0, and then 1. So 1, 0, 0, 0, 0, and 1. X sub 5 column, 0, 0, 0, 0, 1, and a negative 1. And let's see, X sub 6 column, we have zeros, 1, negative 1. Okay, 3 zeros, a 1, and a negative 1, and a 0. And then finally, X sub 7 column. A bunch of zeros, 2 zeros at least, a negative 1, a negative 1, a 0, and a 0. And I'm going to actually pause the video and just double check in a moment, but then we have our right hand sides, 300, 240, 80, negative 20, 30, and 130. And again, like I said, I'm going to pause the video, just double check that I've done everything properly. Yeah, just check that everything works out. Now you can see it's a terribly large system, but it's also known as a sparse system, which means basically that we're lucky. There's a lot of zeros already set up for us. So solving this shouldn't be too bad. I'm going to rope this up. We have a blank piece of paper on the next page, so I'm going to go ahead and paste it there. Copy and hop over, and I'll paste it up top. And move this over. Is it the top? Yeah, it is. Okay, so, and I don't need those columns for X1 and X2 and so on and so forth anymore. So I'll just erase all that information there. We'll get back to that later. All right, Gaussian elimination, here we go. So I want to force this first diagonal element to be a 1, which it already is. So then I'll use that first diagonal element to kill everything below, which basically is only one thing. So I'm going to take negative row 1 and add it to row 2 to become the new row 2. Very fast, easy method. You could, well, let me paste this, copy and paste this, and then I'll showcase kind of how I might have done it if I was doing a very large system by hand. So copy, and then I will paste it here. All right. So if I was doing this actually by hand, I probably would just go ahead and say, well, negative 1 plus 1 is 0. Negative 0 plus 1 is 1. Negative 0 plus 0 is 0. Negative 1 plus 0 is negative 1. Negative 0 plus 0, negative 0 plus 0, negative 0 plus 0. Negative 300 plus 240 is negative 60. And that is pretty quick, actually. Now I'm going to go to the next main diagonal and use that. First of all, I'd like to make it a 1. It already is. Now I'm going to use that to kill everything below. In real world applications, by the way, forcing the diagonal elements to be 0 or 1, is almost already done for you, because generally speaking, those coefficients tell you how many of these objects you have. I only have one street. So they're usually 1s in applications, which is super duper nice. So I'm going to take the opposite of row 2 and add it to row 3 to become the new row 3. Again, you don't actually have to go through and copy and paste all this. Most people will probably do something along the lines of this. Okay, so this becomes a 0 and da 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 da. But I just want to not lose anybody, so I'm going to go ahead and copy this and paste this. So copy, and then I'll scroll down a little bit and I'll paste. All right. And again, we're just taking the opposite of row 2 and adding it to row 3. So opposite of this row, added to this row. Opposite of 0, added to 0, still 0. Opposite of 1, added to 1, 0. Negative 0 plus 1 is still 1. Negative negative 1 is 1 plus 0 is positive 1. Negative 0 plus 0 is negative 0 plus 0. Negative 0 plus negative 1. Negative negative 60, which is 60, plus 80 is 140. And we are now done with 2 of our columns very quickly. Now onto the third column. Again, I would like to take that pivot, is what I'd call that, and kill everything below. Well, that's going to be super easy. I'm just going to take the opposite of row 3 and add it to row 6 to become the new row 6. Again, take the opposite of this row and add it to that row. Again, I will go ahead and copy and paste because I can. If you use a digital whiteboard, that's super nice. You use OneNote or something like that. I don't use OneNote. Some people have asked. I use something called Inkodo, which I find to be kind of nice to use. It has a nice ruler in it and all that fun stuff. I just found that OneNote was a little clunky for what I want to do. All right, negative row 3, add it to row 6. 0 plus 0, 0 plus 0, negative 1 plus 1, negative 1 plus 1, 0 plus negative 1, 0 plus 0, negative 1 plus, negative 1 plus 0 is 1. Remember, we're multiplying that. Row 3 by negative 1, so it's a negative 1 or 1. And again, finally, negative 140 plus 130 is a negative 10. All right. Let's see. So we have successfully forced of 1, 0's below, 1, 0's below, 1, 0's below. There's no way to force that to be a 1. So you're going to have to skip that diagonal element and focus on the next diagonal element. That's a 1. Use it to kill everything below, which means add rows 5 and 6 together to become the new row 6. I don't have a lot of room there, so I will go ahead and copy this and move this upstairs. Hopefully we don't run out of room, but yeah, row 5 plus row 6, 0 plus 0, 0 plus 0, 0 plus 0, 0 plus 0, 1 plus a negative 1, negative 1 plus 0, 0 plus 1, and 30 plus negative 10 is 20. And in this step, I'm actually going to go ahead and force this to be a positive 1 by multiplying that entire row by a negative. All right. And we get down to this. Now, notice we have 1s along the diagonal. If you don't have a 1 in this element, there's just nothing you can do about that. So you move to the next diagonal element, which is this guy, and there. Okay, those are our main diagonals. You can now use those main diagonals to kill everything above. So for an example, I'm going to take row 6, add it to row 5, and then take the opposite of row 6 and add it to row 4. Let me go ahead and state that. So row 6 plus row 5 becomes new row 5, and the opposite of row 6 plus row 4 becomes the new row 4. You can see that this systematic way of doing these problems is actually kind of nice because you don't really run the risk of confounding your work and getting really overly confused. I mean, it is kind of confusing at times, but for the most part, you could do most of this by hand and it's not too terrible. All right, I'm going to zoom in here and we'll take row 6, add it to row 5. So 0 plus 0, 0 plus 0, 0 plus 0, 0 plus 0, 0 plus 1, 1 plus a negative 1, negative 1 plus 0, negative 20 plus 30. There you go. And then let's see, opposite of row 6, add it to row 4 becomes the new row 4. So opposite of row 6, 0 plus 0, that's gone. That's 0. 0 plus 0, well, that's 0. 0 plus 0, that's 0. 0 plus 0, that's 0. 0 plus 0, that's 0. Negative 1 plus 1, well, that's going to be 0. The opposite of negative 1, which is 1, plus negative 1, that's going to be 0, actually. And the opposite of 20 plus 20, so basically 20 minus 20, is 0 as well. You can see this, we have a row of zeros, which means we have an infinite number of solutions, but we knew we were going to because we had way too many unknowns. So that's just a reality, but that's okay. We only have one more step because if you think about it, here's a main diagonal element. We killed everything below. Here's a main diagonal element. We killed everything below. Main diagonal element, killed everything below. We don't have a main diagonal element there, so there's just nothing that we could have done with that. Main diagonal killed everything below. Main diagonal, nothing to kill below. Once we were done with that, we used this main diagonal to kill everything above. If we had things to kill above, we would use this main diagonal to do that. We're about to, actually, we are done. Never mind. I was going to say we can use this to kill everything above, but that's not a diagonal element. The next diagonal element is this guy. There's zeros above, zeros above. We are done. All right. So what does this mean? Well, it means, let's see, remember the columns stood for x1, 2, 3, 4, 5, 6, and 7. So I'm going to start with the bottom row here, and I'm going to say the bottom row tells me that 1x sub 6 minus x sub 7 should equal a negative 20. Well, solving for x sub 6, you get that x sub 6 is equal to x sub 7 minus 20. Okay, which means x sub 7 is free roaming. We don't even know what that is, but we'll see that in a moment. The next row up, we see that x sub 5 minus x sub 7 is equal to 10. That is, x sub 5 can also be written in terms of x sub 7. It's just x sub 7 plus 10. Well, let's go to the next row up. It's all zeros, so that doesn't give us anything. Well, let's go to the next row up. That's x sub 3, so it tells us that x sub 3 plus x sub 4 minus x sub 7 must equal 140. So we're going to go ahead and solve for x sub 3. And you might say, wait a second, where's x sub 4? X sub 4 is also an unknown parameter. Okay, so we'll get to that in a moment. Go to the next row. That's x sub 2 right there. So we have 1x sub 2. Let's see, minus x sub 4 is equal to negative 60. Or in other words, x sub 2 is equal to x sub 4 minus 60. And finally, top row, we get that x sub 1 plus x sub 4, I'll write that in, x sub 1 plus x sub 4 is equal to 300. Or in other words, x sub 1 is equal to a negative x sub 4 plus 300. Now, if somebody said, I need to know what the traffic flow on these streets are throughout the day, and you were tasked with doing this, you could walk in and say, okay, the traffic flow, let me actually copy and paste this so that I can talk about this on another page. So here's the situation. Your boss tells you, listen, I need to know, because I get a lot of complaints from residents in the city that their streets have too many cars going through them throughout the day. And you say, okay, well, we set up some strips, and or maybe your boss tells you this, so you're the hero. Your boss says, I set up some strips and I just need to know, I need you to work out the problem. And you come back and you say, you didn't put out enough strips. And he says, what? You say, well, here's why. You see the traffic flow through Green Street right here. Well, that's going to be 300 minus x sub 4. And he says, well, what's x sub 4? And you say, I'm about to get to that. And he says, okay. Say, okay, well, x sub 2, which is the traffic flow on Orange Street where your boss lives, and he swears it's super busy. You say, well, that traffic flow is actually equal to x sub 4 minus 60. And he says, what is this x sub 4 you keep talking about? And you say, I'm about to get to that. And then you say, okay, but on Blue Street, the situation's a little bit worse. This is why. And you say, because x sub 3, which is the number of cars through Blue Street, is equal to x sub 7 minus x sub 4 plus 140. And he says, wait a second, hold on a second. So now you're introducing yet another variable into this? And you say, no, I'm not. It's just the problem is you need to put a strip on the street x sub 4, which is Black Street between Green and Blue Street. You need to put a strip there so I can determine how many cars go through that street. You didn't put out enough strips. And he says, what? You say, yeah, you didn't put out enough strips. If I knew what x sub 4 is, I could tell you how many cars go across X sub 1, which is Green Street between black and orange. And I could also tell you how many cars go across X sub 2, which is Orange Street between blue and green. Now, if you put a strip on X sub 3, which is Blue Street between orange and black, that's not going to, if you put a traffic strip at X sub 4, which is on Black Street between green and blue, that'll help us find out the traffic pattern on Blue Street, which is X sub 3, but it won't give us the pattern because we still need another strip somewhere else. See, X sub 5, according to our data, is X sub 7 plus 10, and X sub 6, according to our analysis, is X sub 7 minus 20. But we will need a traffic strip also on street X sub 7, which is Orange Street between red and blue. So in the end, we'll need 2 more traffic strips. And you have to pay for them, boss, because you're my boss. You want to put one there and there. Once we know how many cars go through there, I could tell you the traffic patterns throughout this entire neighborhood. And that's how it's done. Yay. So there's how you can set up this system, and that's how you get parametrized solutions from an application like this. Then most applications in a textbook would have the same number of equations as they have variables, but they don't need to. You could still have an undetermined system like this, or an underdetermined system where you have an infinite number of solutions that just allows you to tell your boss, go buy some more traffic strips and throw them out there.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.